Okay, I'm going to solve a couple problems for Chapter 5, starting with 531. Pause for a second, read the problem. Okay, the first thing that you want to do with any problem from Chapter 4 or 5 is to go ahead and draw your free body diagrams, because once you have those set up properly, then all you have to do is say sum of the forces in the x direction is equal to the mass times the acceleration in the x, the same for the y, and at that point it's really just algebra solving for these problems. So actually, before I do the free body diagram, I might as well knock this angle here out real quick. We know that the angle is going to be the inverse tangent of the opposite side over the adjacent side. So I'm going to write this guy up in the corner here for you. 27.76 degrees. Okay, now that I knock that out. Okay, so it asks for what is the force you need to accomplish this, and the one thing that you know is it's talking about the system of the boxes, because both boxes are going to move together at a constant speed. So I can actually, rather than split it up and draw free body diagrams for this guy and then try to marry them together, which is possible, it's just a little bit harder, I can consider this to be my system that the fella is lowering in that direction. So this is going to be my motion, and he's going to be applying some tensional force to his rope right there. So if I consider this to be a system, then obviously my mass of the system is going to be the 32 kilograms plus the 48 kilograms, and that comes out to be 80 kilograms. So let me draw my free body diagram for my system, and I'm drawing it, at the same angle right there. I know that I'm going to have my weight in the downward direction, mass of the system multiplied by gravity, and I know that it's being supported by a normal force, so normal force of the system. That's the force of the ramp pushing up on the boxes. I know I have my tensional force right there, and last but not least, I know that my motion is down the ramp, and so I'm going to have my friction upwards on the ramp, and if you can't read it, that's a little f sub k, k being kinetic friction. So that guy right there. So those are all of the forces that are acting on my system, and of course I want to define my xy coordinate system, kind of like we always do for ramps, where we have the y in that direction and the x in that direction. Once again, the acceleration is going to be along that ramp, all the motion is going to be along that ramp, and it just makes our life so much easier to rotate our coordinate axes. So first I need to break up my weight into the two components, the y component and the x component, and everyone's familiar with that being a similar triangle as that one, so that's going to be the same angle, theta. So in this direction I'm going to have the mass of the system multiplied by the gravity multiplied by the cosine of the angle. And right here I'm going to have the mass of the system multiplied by gravity multiplied by sine of the angle in between them. So what I'm looking for is I'm looking for my tensional force, and if I eyeball this guy up in terms of x and y directions, I'm going to need my frictional force to solve for that. To get my frictional force, I need my normal force. So the first thing I need to do is say, what are the some of the forces in the y direction, I know that it's going to be moving at a constant speed, so my acceleration in my y direction is going to be 0, so is the x. The y direction really says it's not accelerating through the ramp, so my sum of the forces is equal to the mass of the system multiplied by the acceleration in the y direction. That guy is going to be equal to 0. So my sum of my forces is equal to 0. And let me just highlight very quickly my forces in the y direction. Here I have my normal force, and I have my y component of the weight. So I have my normal force upwards minus mass of the system multiplied by gravity cosine of theta. So I've simply solved for my normal force now. Now let me take a look at this bad boy in the x direction, and I say the same thing. Sum of forces in the x direction is equal to mass times acceleration in the x, and again, constant speed means my acceleration is equal to 0. So let me just highlight my forces in the x direction on my complicated diagram here. So I'll change my color. I've got my mass times gravity sine theta, got my frictional force, and I've got my tensional force. So I have my tension upwards, I've got my frictional force, kinetic friction, and mass of the system, gravity, sine theta in the downwards direction. Now, I know what the frictional force is. I know that frictional force is going to be equal to the frictional coefficient, mu sub k, multiplied by the normal force of the system. And lo and behold, I've already solved for that using the y direction. I'm solving for tension, so I'm going to write tension is going to be equal to mass of the system, gravity, sine theta, minus the frictional force, which again, I'm going to plug this guy in right there. Gravity, minus my frictional force, so minus mu sub k. I get my normal force right here. Mass of the system, gravity, cosine of the angle in between them. And now we're at the point where I know what all these guys are. I know what the angle is, I know what the gravity is, I know what the mass of the system is, I know what the coefficient of friction is, mass, gravity, cosine of the angle in between them. I can plug all of those guys in there and come up with a value. That value, I'm going to spare that, writing all that down for you. I highly recommend you do that and verify my my calculation here. You can get the tensional force of the system due to the fellow. So now to solve the second part, what is the magnitude and direction of the frictional force on the second block? It looks very similar. I draw my second block only now, and I know that it has some weight in the downwards direction, some normal force in the upwards direction, and the frictional force is actually going to be in that direction right there, because the box wants to continue, or the box wants to slide off of the lower box. So there's my static friction. I've drawn my free body diagram. Now it is really just algebra. I want to solve for my frictional force. So first thing I want to do is break up my mass and gravity into the two components. So I have the y1, I only care about the x1 right now. Mass times gravity multiplied by sine of the angle in between them. And I say, what are the sum of the forces in the x direction? I know there's a constant speed is equal to mass times acceleration. Acceleration is equal to 0. So I have my frictional force in the upwards direction and in the downwards direction I have mass times gravity times sine of the angle between them. So my frictional force on the upper box is simply going to be the mass of the upper box multiplied by the gravity of the gravity of the system, and then sine of the angle in between them. So 32, 9.8, and then sine of 27.76 degrees. I go ahead and I calculate 146 newtons, and that's going to be up the ramp. So I'm going to work problem 547, take a second to read it. And you know, the great thing about me working this one is because I didn't speak too closely to the radio problems in the lecture. If you looked at the examples, which I certainly expected you to, it talks about these things called period, which is the time of one revolution, and we're given how many revolutions per minute. That's 32. We need the time for one revolution, preferably in seconds. We always work in seconds. So 1 minute multiplied by 60 seconds, and we come up with the 0.53 rev per second. The time for one revolution is going to be the inverse of this. That's the period. Again, one revolution, 1 divided by 0.53 rev per second. We come up with a period of 1.875 seconds. So I'm going to kind of write that up there just to get it out of the way. Now, other kind of housekeeping things we need to worry about is we know that the seat weighs 225 newtons and the person weighs 825 newtons. So let's figure out the total mass real quick. We're going to need that. We know that, you know, weight is equal to mass multiplied by gravity. So 225 plus 825 is equal to mass times 9.8. Go ahead and you divide all that guy out, and you're going to get a mass of 110.2 kilograms. Okay, so now I've gotten some housekeeping out of the way. I'm going to go ahead and erase that and take a look at my person that's being spun around on a little giant swing, you know, game of fun. Got my radius, 7.5 meters, and let me just go ahead and draw my free body diagram for her. Here I have the mass multiplied by gravity pulling her down, and I'm going to have some tensional force in the rope, and I'm going to call that tension B, and I'm going to have my upper tension force, tension A, coming from that rope. And you know, now that I have my free body diagram drawn and drawn correctly, I'm going to choose my XY coordinate system kind of the way that you would think. I'm going to have X going in that direction, Y going in that direction. So let me just go ahead and break tension A up into its two components. Tension A in the Y direction, tension A in the X direction. And I can go ahead and write those very quickly. Tension A in the Y direction is going to be tension A multiplied by, let's see, what's my angle here? That's going to be my 40-degree angle. So that's going to be cosine of 40, tension A in the x direction, tension A, sine of 40. So sum of forces. So looking in the y direction, I'm going to have really only two forces. I'm going to have the tension A supporting that guy and mass times gravity in the downwards direction. So I can go ahead and I can solve for the sum of the forces in the y direction. In the y direction, it is not accelerating. Right, it's not going up or down. So mass times acceleration in the y direction goes to 0. Tension A, cosine 40 upwards, mass times gravity downwards. So I can go ahead and I can solve for tension A. Tension A is simply going to be the mass times gravity, or the weight. So 110.2 multiplied by 9.8 divided by the cosine of 40. So tension A is going to be 1410 newtons. Now I want to look at the sum of the forces in the x direction. And in the x direction, she is, of course, accelerating. Sum of forces in the x direction is going to be the mass times the acceleration. And this is actually the radial acceleration. You have to... And in this direction, I'm going to have tension A in the x direction and tension B. I have nothing to balancing out over here, so it does make sense that she is accelerating. So tension A sine 40, and then tension B. Now I know what my radial acceleration is. My radial acceleration is going to be 4 pi squared capital R divided by the period squared. I didn't get the chance to introduce that in the lecture, but you did again, read that problem, so you're totally familiar with it, of course. So the sum of the forces in the x direction is going to be the mass times that guy right there, 4 pi squared radius divided by the period squared, is equal to that stuff right there. And what I'm really interested in solving for is solving for tension B. So I simply subtract tension A sine 40 from both sides, and I end up with tension B to be equal to the mass times 4 pi squared radius divided by the period squared. Gotta be careful with the t's, minus tension A sine 40. I already calculated what tension A is, so I can plug that guy in right over here. And I know what the radius is, I know what the period is, so now it's a simple matter of saying, okay, this is going to be 110.2 multiplied by 4 pi squared. The radius is 7.5 meters. Period is 1.875 quantity squared, minus 1410 sine of 40, and I get the tension in the B to be 8370 newtons. So again, the hard part of doing this is drawing the free body diagram and then writing Newton's second laws. Solving them is fairly simple.